Okay, here is the second half of 5.4. We're just going to get a bit more practice with rational functions, deal with a few more one-off examples, and just get a little bit more comfortable with all the different possibilities before we start dealing with actual graph sketching, curve sketching, like we did with polynomials. So before we start that, let's get into a few examples. The first one says evaluate the limit as x approaches 0 of 1 over x. We already know roughly what the graph looks like, hopefully. But let's take a look and let's talk about how we would evaluate the behavior around the asymptote. So in order to do that, we're just essentially looking at the limit. And this is just review back to, I think, 4.3 or 4.4 when we talked about limits for 1 over 0 kind of problems. And we said all we do is we just look very close to the left and to the right of that asymptote, and we just try and figure out what's going on. So we're just going to sub in values very small right around to the left of x equals 0 and just to the right of x equals 0. So for the left, we could do negative 0.1, and that would be 1 divided by that would be negative 10. If we did negative 0.01, it would be negative 100, negative 1,000, negative 10,000. So it looks at, like, as we go to the left, we're approaching negative infinity. Looking to the right, let's do the same thing. We'll pick small numbers. Start with 0.1. We divide that 1 over that. 1 over 0.1 is 10, or 100, or 1,000, or 10,000. And so from that side, we're approaching positive infinity. So hopefully you already know what this should look like, but just this kind of confirms on the left of our function, we start approaching negative infinity. And on the right, as we get closer to our asymptote, we approach positive infinity. So essentially that's how our graph looks. And like I said, I'm sure you guys know what a 1 over x function looks like already, but just in case, you can use that for any type of rational function. You can use that to help you try and define what's going on around a vertical asymptote. It will tell you the upward and downward direction, so that it could be a valuable tool in your tool belt. So next one, let's deal with another limit problem. Yeah, limits will come in very handy here. So we're going to deal with some different ones just because it's been a while. With this one, the limit as x approaches negative 1 for x cubed plus 1 over x plus 1. Now, in this case, we know that if we plug this in, that's going to be negative 1 cubed plus 1 over negative 1 plus 1. So that's going to be equal to 0 over 0. So we know we can't do that. But we know that with 0 over 0 types, those are indeterminate forms. So we can use a bit of know-how to help us out. So let's try this again. The limit as x approaches negative 1 of x cubed plus 1 over x plus 1. We said one of the things that we can do is we can try factoring. And hopefully you remember that x cubed plus 1 is one of our special factoring rules. So let's just use that rule. In fact, as it turns out with that one, that just factors to x plus 1 times x squared plus x, x squared minus x plus 1, all over x plus 1, our original denominator. So in this case, those two, the x plus 1 and x plus 1 are going to cancel. And so the limit as x approaches negative 1 is going to be x squared minus x plus 1. We've gotten rid of that denominator, so now we can just plug in and solve. So now that's going to be negative 1 squared minus negative 1 plus 1. Because that's going to be 1, that's double negatives, that's a positive plus 1 plus 1. So that will be equal to 3. And that's all there is to that one. So if it's 0 over 0 or some sort of other indeterminate form, try using one of our algebraic methods to simplify and get rid of that denominator in order to deal with that asymptote. And you'll see how that comes in handy in a later problem in this lesson. But for right now, let's continue on. Let's talk about infinite limits with horizontal asymptotes. So we're talking about the limits as x approaches positive or negative infinity. So horizontal asymptotes. So by subbing in positive or negative infinity into h of x using the limit as x approaches infinity of h of x, the result will give infinity over infinity, indeterminate. So again, this is another indeterminate form, so we can use some new algebraic methods to help us out a bit. So with this one, what we're going to do is we're going to take a look at the problem we have here, and we're going to look in the denominator, figure out what's our highest power. In this case, it's x squared. So we're just going to divide everything out by x squared. So we're just going to rewrite this whole fraction, and we're just going to take each term and divide it by x squared. And you're going to see why this works in just a second. 3x squared over x squared plus x over x squared minus 6 over x squared. Now, let's go through and simplify. Oh, by the way, we forgot our limit statement because that's really important because we didn't just get rid of that. That has to stick around. So that's the limit as x approaches infinity. And what happens here, let's go term by term, with 6x squared over x squared. The x squareds cancel and we're left with just 6. With 2x over x squared, if we were to do infinity, or oh, actually, you know what? Let's not go that far just yet. Let's talk about. So let's just divide out those x's. That becomes 2 over x over x squared, and then in the denominator becomes 3 plus 1 over x minus 6 over x squared. Now, I know this is going to sound a little counterintuitive, but I just want you, we're going to go through each term and we're going to see what happens if we were to plug a really large number into each one. We're going to pretend like we could sub in infinity, even though we know infinity isn't an actual number that we can work with, that we can plug into our calculators. So let's go term by term. The 6 just stays as a 6. If x is approaching infinity, 2 divided by some really large number, that's going to get really, really close to 0. So if we did 2 divided by a million, it would be close to 0. 2 divided by a billion or a trillion or a Google or Googleplex or however big you want to go, that would become 0. And the same thing with 1 over x squared would be a 0. Then on the bottom, the 3, we can't do anything with that. That just stays as a 3. Then we have 1 over x. So if we got a very large number close to infinity, that would be 0. And then the 6 over x squared would also be 0. So in this case, we're left with 6 over 3, or 2. So as it turns out, with this function here, the horizontal asymptote for this one is actually going to work out to be y equals 2. So this is called the quotient law for limits. So if a, l, and m are real numbers, and limit as x approaches a of f of x is equal to l, and the limit as x approaches a of g of x is equal to m, then the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f of x over the limit as x approaches a of g of x. It's equal to L over m, where m cannot equal 0. So note, if the highest degree of the rational function is on the numerator, your limit will be infinity, as you will have something like this here. This could be the original function, and when we divide everything out by the highest power, it looks something like this. And since we have the top going towards infinity, and everything else in the bottom either being a whole number or a zero, then it's going to be infinity divided by some small number. So it's going to be infinity. So basically, if the degree is higher on the numerator than the denominator, then your limit's going to be infinity. It's going to be some sort of oblique asymptote or something else. If the degrees are the same, then we can have a horizontal asymptote, and we can use that method to solve. Okay, continuity. This should all be a review right now. Just think back in, I think this was 4.4. We said that a function f of x is continuous at x equals a if and only if, by the way, that's what that means there, if and only if, the limit as x approaches a of f of x is equal to f of a. For the function to be continuous at x equals a, the following conditions must be true. The limit has to exist at a, the function has to have a value at a, and the limit has to be equal to the function. And we said that a function can be considered continuous if every single point is continuous. So if every single point along that function follows those three rules, follows those three conditions, then the whole function is continuous. So the next part of the lesson is just kind of fill in the blanks. It should be self-explanatory, so I'll read through really quickly and we'll continue on. So example 1, find all number s for x equals a for which each function is discontinuous. So it's asking us to find any discontinuous points in each one. So f of x equals x over x plus 2 squared. The denominator x plus 2 squared is 0 when x equals negative 2. Just set it equal to 0 when solved. This means the function is discontinuous at x equals negative 2. The line negative 2 is a vertical asymptote. F of negative 2 does not exist, and the limit of as x approaches negative 2 of the function does not exist. Conditions 1 and 2 are not satisfied, 1 and 2 that we read on the last page. For question B, f of x equals x squared minus 16 over x plus 4. First, we can factor, which I've shown above. The denominator is 0 when x equals 4. The graph of the simplified function is f of x equals x plus 4, which we found by factoring and then canceling out the terms. There is a hole at x equals 4. F of 4 does not exist, therefore condition 2 is not satisfied. So essentially this graph is going to look like the same as the function y equals x plus 4, but with that additional restriction. And lastly, we have a piecewise function, f of x equals x cubed plus 1 if x is less than 0, or x squared plus 7x plus 1 over x plus 1 if x is greater than or equal to 0. Since x cubed is plus 1 is the first part, it's a polynomial function. F of x is continuous for x is less than 0 for the region that it occupies. The function is continuous for x is less than 0. X is an element of the real number set. The other part, x squared plus 7 plus 1 over x plus 1, has a discontinuity at x equals negative 1. So it could potentially make it discontinuous. But the domain of the function is x is greater than 0. Therefore, it's continuous for x is greater than or equal to 0. That the only part of the function where it might be discontinuous is at x equals 0. The function is continuous if the limit as x approaches 0 of f of x exists, and the limit as x approaches 0 of f of x is equal to f of 0, which we've shown in this section right above. Therefore, all three conditions are satisfied at x equals 0. F of x is continuous for all values of the domain. So for this section here, I'll go back and clarify a little bit. Okay. So we saw there was discontinuity at x equals -1, but according to our piecewise function, x equals -1, our function is not that part of the function does not show up in that part of the graph, so it doesn't really come into play. So really, the only spot where we might have a discontinuity, a hole, is where we join those two functions together. X is greater than or equal to 0. So we just have to check that spot. So we're going to find f of 0 for the first half, which we do up here, and for the second half. As it turns out, they both equal 1, which makes it that they join up, which makes the function continuous. So the first part of the function is continuous. The second part of the function is continuous over the region that we defined for it, and they join it to the same spot, so the whole thing has to be continuous. So last part of this lesson, we're going to talk about removing a discontinuity. So determine a point of discontinuity for f of x equals x squared minus 6x plus 8 over x minus 2. So you'll notice that this is a quadratic over a linear. So let's just try factoring and see what happens. So if we take that and we factor the top, that's going to work out to x minus 4, x minus 2 over x minus 2. As it turns out, those two cancel. And it works out to f of x equals x minus 4. But we still have that restriction to worry about because it's not actually x minus 4. It's this function here, and we still have that restriction on the bottom, so we have to factor that in. So x cannot be equal to positive 2. We can examine the limit as x approaches 2 from the right of f of x, and the limit as x approaches 2 from the left of f of x to determine what f of x should be. Or, that would be the long way of doing it. We could try and find some small values, like we could plug in 1.999 and 2.001 and try and plug those in. Or we can just use the original function because we know it should follow the same behavior. So x minus 4. So f of 2 is going to be 2 minus 4, or negative 2. So essentially, what the graph is going to look like is the same as x plus 4. So here's 4, slope of 1. But x equals 2, we're going to have a hole. Therefore, we can redefine the function to remove the discontinuity. So we could rewrite that as f of x is equal to x squared minus 6x plus 8 over x minus 2, where x cannot be equal to 2. And then for the spots where we have that for that hole, we define it as negative 2 at x equals 2. That's pretty much all there is to that. Like I said, lots of little bits and pieces, stuff that might come in handy once in a while when you're trying to graph rational functions. Next lesson, we'll take all that, add our knowledge from polynomial functions, and turn it into a comprehensive method for graphing rational functions. So we'll take care of that in 5.5. In the meantime, practice all these skills, and hopefully by the time we get there, you'll have everything you need.